that's how we get a sound that we're trying to create. And so if we're talking about like a musical instrument, you get, when you play a musical instrument, a certain sound is made, and that sound is made because of a standing wave. And so if you're playing a flute and you are blowing across the hole there, what keys you have pressed down will dictate how long, it kind of becomes how long the tube is, and it'll be a certain sound based on that. If you play a guitar and you pluck a string on the guitar, it will, based on the type of material that that string is made of and the tension that you have that string, will determine what sound is made based on kind of where you're putting that with the frets. And so anytime you're playing an instrument, you're relying on this idea of resonance in order to get your sound from that. And so we're going to look at the physical properties of what happens with that. And so in the way of sound, a standing wave is going to amplify that single frequency at that given length. And so it's the one that you hear. When you're playing, or when you're, let's say you're playing a trumpet, you're putting in a whole bunch of frequencies, and the one that resonates is the sound that you hear. It's made louder, and I'll show you that with what we do today. So what happens is we've got two different types, or well, there's actually three different kind of ways that we look at this. We're going to focus on kind of two of them. We have a string, and then we have tubes. And so this is where we're going to get different sounds. Let me grab one thing. I got more than one thing. Here we go. So when you play a flute, by blowing through the mouthpiece of the flute, there's a whole bunch of frequencies that are made with that sound. It's called white noise. It has a whole bunch of, it's just sort of like there. But when you blow through this, a whole bunch of frequencies are created, and depending on which hole you have open, will depend on the sound that you make. And so if I play this like this, so as I do that, the note gets higher as I open up holes along the flute here. If I take a slide whistle, if you're bored someday, YouTube to look at SpongeBob and SpongeBob and Patrick, the slide whistle episode. It's hilarious. So if you're just like, what should I watch? SpongeBob with a slide whistle is really funny. And so what happens there is as it gets longer, you hear the lower sound, and it gets shorter, you hear the higher sound. SpongeBob and Patrick use it to, like, as people are doing things. So if someone's there, they're like, oh, what's wrong way? I did it backward. Like up and down and stuff. It's super funny. Same thing happens if you're looking at a xylophone. You can hear, this is just a little kid's toy, but you can hear differences in the sound there, and same thing. Each one has a different sound. That's all based on this idea of resonance, and everything has an ability to resonate at a given frequency. When I knock on this table, it has a specific frequency. If I flick this specific frequency, I don't know, let me try it. I can usually do it even on my head. No, not with a mask, okay. Everything has a specific resonating frequency if it's a rigid object of some sort that can do that. And so what we're going to look at is how this works in standing waves. And what we looked at last week was this idea of the way that waves add up on each other. We looked at it before break, and then we reviewed it just briefly as we were wrapping up last week. And so you have waves that come on the same side. They're going to add up on each other and just build up for a moment and then continue. You have waves on the opposite side. They're going to cancel out for a moment and then continue. And if you send repetitive wave pulses, you'll get a standing wave. I'm going to go ahead and turn this on here. Maybe, there we go. And so this is just a wave generator here. It's making this little bar here go up and down. I'm going to change the frequency on here. And you can see that I have a spot here that's really moving up and down a lot. I have another spot here that's moving up and down a lot, and I have another spot here that's moving up and down a lot. This is a standing wave, and it only happens under certain circumstances. And so when you have a standing wave, I'm going to draw this on here real quick. Draw this right here. Oh, there it is. So let's use a string for example. When you have a standing wave, you'll have it go up and down like that. So if this is just a regular wave, I would have two wavelengths. Right? Here would be one wavelength, here would be the next. And that stays true. But what happens is, it's also reflecting back, and we create this everywhere it goes down, it's also coming back and going up. And so we have these areas that are moving a lot, and then areas that are standing still. So this still has two wavelengths that are present here. These spots where it's not moving, these are called nodes. So all these little spots here that aren't moving are called nodes. And so in this one we would have 5 nodes. The other thing is, this spot where they're moving a lot, those are called antinodes. So where it's moving a lot, it's called an antinode. Where it's nice and still, it's called a node. And this will help us determine what those requirements are in order to make a standing wave occur. In a string, you have different options of the way the way it goes. So if we have a string here, when you have a string, it's a node on both ends. So if it's a string, you have a node on both ends. That means you have a spot, like here could represent a string. There's a node on both ends. It's the part where it's moving the least. So again, if you play a stringed instrument, and you pluck on that string instrument, or you draw a bow across it, you're creating a standing wave. Usually is just set up like this. So there's only one way. Well, there's lots of ways, but the main way will be from the first node to the first node. So just between 2 nodes here. And it would look something like this. Just like that. If this were shorter, we wouldn't be able to have the nodes. If it were longer, it wouldn't fall on the nodes. So it will only fall specifically, the only time you're going to get resonance is specifically when you have those nodes. We can identify that resonance when we're using sound because it gets loud. It's the note that you'll hear. Now I can take this same note or the same string and instead of going from the first note to the second note, I can do something like this. It still starts on a node and ends on a node, but now I have another node that's present in the middle. I can do it again. Same string, and most of these end up, like I can force it here to make this happen. If I just play it, it'll be this first one. But if I take and I drive it from another frequency, it will still resonate on these other ones here. This one, let me get this on here decently. Looks like this. standing wave that has kind of 3 parts to it. And I could keep on going. If we look at this one here, it's got 4 parts to it. And this one, I said, is 2 wavelengths. Because we have the wave here, and then it's just flipping up and down. And the wave here, flipping up and down. So this one here is, you have 1/2 of the wavelength of your wave that's playing in this one. Here, you'll have 1 wavelength. So you got here the top and the bottom, and then it's flipping up and down. Here, you have 3/2 of your wavelength. So 1.5, and it always goes up on the half. So if you have a string, anytime you have a string, you have a node that's present on each end, and the only way that a sound will resonate is if it has the wavelength required to meet this criteria. So if you have a given wavelength, and half of that wavelength is the length of that string, it will resonate, you'll hear it loud. If it's not, you're just not going to hear it. It's not something that's going to be there. That's the first part. Tubes, actually I'll give you the equation that goes with this. The equation that we use with this, we have frequency, and I'm going to put a little n here, it's a subscript n, because there will be, this would be one frequency, this would be a different one, this would be a different one. And I'll talk about what that n means in a moment. Is equal to n times v over 2L. N can be 1, 2, 3, any whole number here. And if we look at this, the speed over our wavelength gives us our frequency in general. 2L would give us a full wavelength. So if we say n is 1, we're talking about here, 1 over 2L, 1 over 2 is 1/2. When we say n is 2, we say 2 divided by 2 would give us 1 wavelength. If I say n is 3, 3 over 2 gives me 3/2, so 1.5 wavelengths. So n essentially will allow us to step up the number of wavelengths we have in order to meet the requirement of that frequency we need to hear. Same thing happens in tubes. So let me, before we move on to tubes, I'm going to just take and I'm going to change the frequency on here. If I go up in frequency, anytime my frequency goes up, my wavelength is going to go down. So if you look here, I've got 1, 2, 3, 4, 5 spots that it's moving up and down. See if I can go up, see if I can go down a bunch. There's 3 what we were at before. Didn't like that very much. It's a little loose, but you can see here that I have half a wavelength and half a wavelength. So I have a single wavelength right here. I don't know if I can get it down to just one that actually. If you ever jump rope, you're creating a standing wave. It's just like that up top. It's going up and down and up and down and up and down. So I'm going to turn this off. We're going to talk about tubes now. There's 2 types of tubes that you can experience here. One of them, we'll say open both ends. And then the other one is closed one end. These are the 2 that we're going to focus on. So open on both ends would be something like this, where you can take it, you can look through it, and when you look through it, you can see the other side. Closed one end implies then that it's open on the other. Be something like this, where I've got an open end here, closed end here. Both of them will resonate, but both of them will be they're different in the way that we'll solve for that. When we have tubes, when we have an open end, open ends have antinodes. In order for resonance to happen, the open end would have an antinode and a closed end has a node. So the open end has an antinode, the closed end has a node. And so we'll look at it like this. I'm going to draw 3 different ones, and we'll draw the waves in there of what they could show up as. And then I'm going to show you on some of these how this works. So open both ends. Look like this. Would be 1, 2, 3. So 1, 2, 3. Closed one end, I can draw it the same way. You can even go with the same length, but I'm going to put a closed end on one of them. So I'll do that 3 times here. I'm actually not going to number them at this point. We'll number them in a bit. So let's look at our requirements for what these are, and we'll draw these waves in there. So for a tube that's open on both ends, it means we'll have an antinode on each end. So an antinode, if we go back here, is this wide part that we're going to experience. So it's sort of a weird way to start when you're drawing it on there. However, if I just were to take kind of this middle section here, you're going from the open spot where it's the widest to a node, and then to the widest part again. So if I move that to what I'm experiencing here, it looks like this. So this is that node that's in the middle. This is a half of my half, so a fourth. This is the other fourth. It gives me a half wavelength here. And I'll just write that here. Like that. If we do the same thing on the next one, instead of going right here, I'm going to take and go from an antinode. I'll keep another antinode there and go to the next one. And it would go through like that. So I'm going from an antinode, I'll hit a node, I'll have another antinode and another node, and I'll end on an antinode. So if I put my antinodes in there like this, look like that. Because if we're following a single wave, if I go from the peak here down to the trough and back up to the peak, that's a single wavelength. I can do it again. Down on the third one, I'm going to use this as the example still. Take this off. And what I'm doing here, if I move this down here to the next antinode, I've got 3 nodes that are in the middle. I started an antinode and I have a node, antinode, node, antinode, node, antinode. And I end on that last antinode. So it looks something like this. It'll look something like that. In this case, I've got 1.5 wavelengths. So I can again say 3 halves of my wavelength there. Sometimes people like to talk about them as bubbles, and that's fine too. This would be 1 bubble, this would be 2 bubbles, this would be 3 bubbles. Anytime you have a bubble, you're using 1/2 of the wavelength. So if I look at this, I have 1 bubble, it's 1/2 of the wavelength. Here I have 2 bubbles, I've got 2 halves, so 1. 3 bubbles, I've got 3 halves, so 1.5, however you would want to do that. Same thing comes over here. If each bubble is half, then each half of that is a fourth. So I would just have 1 a fourth and a fourth giving me a half. Here I would have my half, and a fourth would give me one total. Here I have two halves, and then the fourth and the fourth give me another half. So just keeping in mind that each of these bubbles is sort of equal to half of the wavelength. Let's look at what happens with the closed end. On the closed end, we start with a node on the closed end and an antinode on the open end. So if you go just from the first node to the first antinode, you're only getting 1/4 of that total wavelength in there. Because if this wave, this is just that up part, then it would come down and it would go way down and be all the way down here to get that full wave. So here, I've got 1/4 of the wavelength. The next one, it'll look something like this, where I go from a node, I go to another node, and then my antinode out. So it would look like that. I have a half, and then another half of a half, so another fourth. This would give me 3/4 of my wavelength here. Again, keeping those pieces in line, those qualifications in line, if I went to the next antinode, it would look something like that. I'd have a half and a half to give me a whole, and then another fourth, and I would have 5/4 of my wavelength. So let's look at how this compares numerically. Here we went from a half to 1 to 1.5, we go to 2 to 2.5 to 3, and this was our equation where n could be 1, 2, 3, 4, 5, whatever, and that you're going to get on. Cool. Guess what? This equation is the same here. There is a little difference, and I'll tell you that in a minute. So the same equation holds true. F of n equals n v over 2l, where n is equal to 1, 2, 3, etc. But that same pattern can't hold true in the next part because we go from 1/4 to 3/4. To 1 1/4 to 1 3/4. So we go up by halves, but we're going up by halves, landing on the fourths. So the equation for closed at one end is this. F of n equals n, I'll step out in a second, v divided by 4l, and the n can only be 1, 3, 5, 7, 9. It can only fall on those odd numbers. 1, 3, 5, 7, etc. What that does in doing that is it 1, so if n is 1, we've got 1/4 of our wavelength. N is 3, we've got 3/4. N is 5, 5/4. It still follows that same pattern. You can have a tube that is closed on both ends, but it behaves like the string does, so we don't really do much with that. Is it possible? Absolutely. Do we do much with it? No. Here's the difference between these two. The equation is the same. When we're talking about a string, the V we'll use is the speed of sound in the string. And that's goofy because that's going to depend on the tension of the string, what the string is made of, stuff like that. And so that is usually, if it's a string, either A, they'll give you what the speed is in that string, and then you'll calculate from there, or they'll give you other information and you'll have to go back and calculate it. It will not be 340 meters per second when you're talking about a string, because the sound is coming from the vibration of the string, and so that's where it's originating. When you're talking about a tube, in either one of the tube equations, you'll use the speed of sound in air. Because it's causing that sound is causing vibrations in the air, and it's those vibrations in the air that are resonating. And so when you're dealing with these, the V on both of these is 340 meters per second, unless given otherwise, but most of the time we'll stay right with that. So all the equations look pretty similar, but it's knowing some of the little pieces on exactly what's happening and how you can calculate from there. The thing that happens with this, first of all, in your practice problems, I have like on half the sheet you have the practice problems. On the other half, it'll give a printed summary of this. So if you feel like you might be missing something or if you're not sure, that's there for you to work alongside. The biggest thing is knowing exactly what kind of situation you're using, and they each sort of have their own little thing. So what I want to do is show this in a couple different ways, and we'll do some calculations here. I will be taking this down in a moment, so why don't I do this? If you want to take a picture of that, I'll just give you a moment to do that. Don't feel like you have to, but if it's helpful, go ahead and do that. I know a lot of you have it written down. And then I am going to erase it. We're going to do some calculations here. First of all, we'll calculate this sound. So we'll take, if I take one of these little whirly tubes, let's see, can I do it this way? You can hear kind of two different frequencies. If I go faster, a little bit. So the range of frequencies that I'm creating by spinning it continues to change, but this still picks up certain frequencies based on the way that it's structured. So this first one, that lowest one, only had a half of a wavelength in it. The next one had a full wavelength in there, and then 3 halves. These two have different lengths. They're just about, I don't know, about 8 centimeters off. And so if I take the pink one, it has its own frequency. Lower one. I don't think I can go lower than that. And then you can keep going up and down and stuff. But it's not a constant, it's not like the slide whistle where it's like whoop. It has its wet one or the next, whatever that looks like. So here's what we're going to do. I'm going to measure this, and we're going to calculate what those frequencies are for this one. Maybe. There we go. So the length on this one is 70 centimeters. So this does need to be in meters, so 0.7 meters. And we're dealing with open at both ends. So I'm going to take all this down. So 0.70 meters, so L, so this is open both ends. Our length is 0.70 meters. Speed of sound in air, this is a tube, so we'll use the velocity of 340 meters per second. And the equation that we'll use is f of n equals n v over 2l. And so we want to find the first 3, we call them harmonics, first 3 harmonics in which it plays. So we can do this. We can say f of 1 equals 1 times 340 over 2 times 0.7 meters. And when you put it in your calculator, you do have to be careful that you don't just put it all in one line. Because what will happen if you do that is that your calculator will take 340 divided by 2, it'll get an answer, and then it'll take that answer times 0.7. But you want to take 340 divided by this whole thing. And so when we do that, so 340, 2 times 0.7 is 1.4. So we can just go 340 divided by 1.4. We get 242.8571. We're just going to say 242.9. And it's hertz. 242.9 hertz. So when I swing this one, just plain, without hitting things, that real low one that you hear, right about 242-ish, somewhere between 242 and 250 hertz. We can figure out the next frequency. The next frequency will fall when n equals 2. So we'll say f of 2 equals 2, 340 over 2 times 0.7. So I can just take that number times 2. I get 485.714, a long number, we'll say 485.7 hertz. So when I swing this and it's the lower one, we're at 242.9 hertz. When I make it go faster, 485.7. So we can calculate those. We'll do f of 3. I don't know if I can swing it that fast, but we'll give it a try. The only reason that pink one is shorter is because I wasn't swinging it fast enough, and someone else was, and then they snapped it off. So it's a balance to get it to work. So times 3, again, same thing, 340 over 2 times 0.7. So if I take that, 340 divided by 1.4 times 3, 728.57, so 728.6 hertz. So these are the different frequencies that you'll hear. Again, based on this specific tube. So we can take this, lower one, middle one, we do it. There we go, higher one. If I could swing it faster, I could get it higher, we could go from there. And each time you're just changing the end. Again, it's not a slide whistle. It's not a constant up and down, but it is these steps up based on meeting that criteria of having an antinote at each end. The same thing happens with closed-ended tubes. We're going to do the same thing here. We're going to say tube closed at one end. Therefore, it's open at the other. O-P-E-N. There we go. There we go. And so what we're going to do this time is we're going to measure what this, what the height of this is. And then from there, I'll set the frequency. I'll show you kind of where resonance takes place and how it sounds different than it just being in general. So if we take the meter stick and measure the length of this tube is exactly half a meter tall. So we'll do the large one first. Here, L equals 0.50 meters. We know that V we'll use is 340 meters per second, and this time we're going to solve for, we're just going to solve for f of 1 and f of 3. Remember that when we're talking about using the open at one end and closed at one end, it only falls on the odd numbers. So the first two harmonics available. The first one is n equals 1. The second one, well over here it would be n equals 2. It's not a possibility with this one. So it's 1 and 3. And so we say f of n equals n v over 4l. We don't need to rearrange anything here. We don't need to rearrange anything here. And so we'll do f of 1 equals 1 times 340 over 4 times 0.5. We'll get that, and then we'll do it again for f of 3 equals 3 times 340 over 4 times 0.5. So we'll calculate out both of those. Thank you. And the first one we get 170 hertz, and then we get 510 hertz. 170 hertz and 510 hertz. Now, this is going to be a pretty good estimate. The thing that happens is this is based sort of on an average air temperature. We may, if we're a little bit higher or a little bit lower, our frequencies would have a similar response there. But what I'm going to do is turn on my speaker here, and I'm going to go pretty low. Wrong thing. I'll start just at 100 hertz here. Come on, little speaker. There we go. Okay, so here's my speaker. It's right at 100 hertz. You probably can't hear much. And when I move it over here, it doesn't change much between that and that. Now what I'm going to change, I'm not going to change the volume. I am going to change the frequency. And what you'll hear though is this get really loud. Again, I'm not touching the actual volume here, it's just the frequency. So I'm at 100 hertz. I'm going to go ahead and turn that up. You hear how that got loud? This is the same sound here. This is the same volume that I had it at. But it gets real loud. Not because I've affected the volume, but because this frequency is what's resonating here. We calculated and predicted at 170 hertz, 166 hertz. Really, really close. In fact, for using a real average number for the speed of sound, that's really close. But now I can take, I'm going to jump up to 510. So I'm right at 486 right now. That is pretty loud. Annoying, right? I was at 501 hertz. Again, really close to that 510. In fact, if you take the 166 times 3, it's even closer. So every time you're hitting one of these resonant frequencies and hitting these different harmonics is when it gets loud. And so here, when I'm doing this, I'm feeding a single frequency in there. If that frequency is one that it'll resonate with, it gets loud. If it's not one that'll be resonating with it, it doesn't get loud. And the way that that's different here is with something like a whistle. When you're blowing air through a whistle, it creates a whole bunch of frequencies. But the one that gets picked up is the one that is the resonant frequency, and that's what you hear. The next thing we're going to do, I'm going to do another one that's like this, but this time I'm going to use this tube, and we're going to come up with, we're going to calculate for L. So I'm going to show you how to calculate for L. We'll go through the rearrangements there, and we'll talk about what that looks like. So, I need to quickly do this, just to make sure I get it in the right range. Come on. when it gets loud, and we're gonna stop at that one for a moment. And then from there we'll calculate L. Okay, so I'm gonna start in the upper 200s on this. Again, not the best sound in the world. We're gonna go up, and when it gets loudish is when we'll stop it. Nice and loud there? Yeah? Is that okay? We'll go with that one? We're at 193 hertz is where it got real loud. And you could hear that volume getting up. Just because the frequency is getting close to there, you start to have some partial resonation there. So we're going to use 193 hertz here. And when you're just, usually, well, this one I'm setting up is N of 1. If nothing is given about the N to use 1. So it just says determine. Sometimes it'll say the resonant frequency. Sometimes it'll let's call it the fundamental frequency. If it's any of those things, use N of 1. So we'll say V equals 340 meters per second. This time, we're going to say F of 1 equals 193 hertz. N equals 1. And we're going to solve for the length. And we're going to see how close we get. So we have F of 1 equals NV over 4L. And to solve for the L, and for both equations, you'll rearrange the solving here. We'll leave N here for a minute. Well, you'll rearrange it the same way. So to do that, you'll multiply both sides by L first. You can leave the 4 there. And then you'll divide by F of N. In doing that, you'll get rid of the L over here. You'll get rid of the F of N over here. And you'll be left with L equals N times V over 4 F of N. So really, if you're just looking at the equation, the L and the F of N are switched from each other. So now we can put our information in here. The length is equal to N is 1, so 1 times 340 over 4, and our frequency was 193 hertz. Again, keep 4 times 193 on the bottom. So 340 divided by parentheses 4 times 193. We end up with 0.44 meters. Would be how long that tube should be. We take and we measure it, drop this in here, it ends up just past 0.42. Again, 340 is a really kind of a broad estimate. So 0.4, 0.42, it's pretty close. If we wanted to get really specific, we would take our air temperature and we would use that to determine exactly what the speed of sound would be. And then we could work from that. We're not going to get that specific with what we do. So I'll step out of the way, take this down so you can get anything else that you're missing. And then as we're getting into this next week, this week, obviously today we're doing this. On Wednesday we'll do the lab, then we'll wrap up everything inside, like all the pieces of this. And you'll quiz on Friday. It'll be the first quiz of the quarter. Second thing, then next week, we're going to build instruments next week. You can build them as complexly or as straightforward as you choose. Normally when we do this in class, it's a much bigger production, like when we can all be in each other's space a little bit more of just like building and doing and all that stuff. We will keep it simple. Whether someone's at home or at school, they'll have the same task. I'll have supplies here for you to use in class.
Good afternoon. Please excuse this interruption.